This is part 4 of linear differential equation with constant coefficients. In this part 4, we are going to study how to find particular integral of a given differential equation when its right hand side x is e raised to ax. To understand this video properly, I suggest you to watch earlier 3 parts of my videos on the same topic, the links of which I have given in the description box, because in the present video I have to take direct references of those 3 videos. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. We have d e raised to ax is derivative of e raised to ax, which is a e raised to ax. D square e raised to ax is a square e raised to ax. D cube e raised to ax is a cube e raised to ax. So on and so forth. D raised to n e raised to ax is a raised to n e raised to ax. We observe that after derivative, d is replaced by a. So fd e raised to ax will be d raised to n p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus so on and so forth plus pn into e raised to ax, which will be e raised to ax plus p1 d raised to n minus 1 e raised to ax plus p2 d raised to n minus 2 e raised to ax plus so on and so forth plus pn e raised to ax. This will be, according to these values which we have already found out, will be a raised to n e raised to ax, this value, plus p1 a raised to n minus 1 e raised to ax plus p2 a raised to n minus 2 e raised to ax plus so on and so forth plus pn e raised to ax. Now taking e raised to ax common from each term, it will be fd e raised to ax equals an plus p1 a raised to n minus 1 plus p2 a raised to n minus 2 plus so on and so forth plus pn into e raised to ax. Here we observe that when fd operates on e raised to ax, this d is replaced by a. See here, d is replaced by a everywhere. I'm sure you know what are p1, p2, p3, so on and so forth, pn. These are the constant coefficients of the differential equation. So what we get here is fd e raised to ax equals f of a, which is this, into e raised to ax. Now we will operate 1 upon fd on both sides. So it will be 1 upon fd into e raised to ax equals 1 upon fd into fa into e raised to ax. Now 1 upon fd and fd are inverse operators, so they cancel each other out, and what we get is e raised to ax equals fa into 1 upon fd into e raised to ax. By writing 1 upon fd into e raised to ax on the left hand side, this will be 1 upon fd operating on e raised to ax is nothing but this fa operating on this e raised to ax. Here observe that this d is replaced by a. So particular integral is operating 1 upon fd on e raised to ax, that will be 1 upon fa e raised to ax, where we have replaced this d by a. For example, let us find particular integral of differential equation d square plus 2d plus y equals e raised to 2x. Here fd is d square plus 2d plus 1. So particular integral will be 1 upon fd e raised to 2x, which is 1 upon d square plus 2d plus 1 e raised to 2x. Here we have to replace this d by this 2. So we get 1 upon 2 square plus 2 into 2 plus 1 e raised to 2x. So the particular integral will be 1 upon 9 e raised to 2x, e raised to 2x upon 9. Let us see how to find particular integral of differential equation d cube minus 3d square plus 4y equals e raised to 3x. Here ft is minus 3d square plus 4. So particular integral is 1 upon fd into this e raised to 3x, which is 1 upon d cube minus 3d square plus 4 e raised to 3x. We have to replace this d by this 3. So it will be 3 cube minus 3 into 3 square plus 4 e raised to 3x, which is 3 cube minus 3 cube will be 0. So particular integral is e raised to 3x upon 4. This formula of particular integral holds as long as this fa is not 0, because then this method will fail. We will see one example of this type. We will see how to find particular integral of differential equation d cube minus 2d square minus 5d plus 6y equals e raised to 3x. fd is d cube minus 2d square minus 5d plus 6, which can be factored as d minus 1 into d plus 2 into d minus 3. How to find factors of a cubic polynomial I have explained in my earlier parts on the same topic. Here this factor d minus 3 suggests that f of this 3 will be 3 minus 1 into 3 plus 2 into 3 minus 3, which will be 0. And since f3 is 0, we cannot apply this method because particular integral will be 1 upon fd e raised to 3x equals 1 upon f3 into e raised to 3x. That will be 1 upon 0 e raised to 3x. Here, because of this 1 upon 0, this method fails. So what we do is we write particular integral equals 1 upon d minus 1 into d plus 2 into d minus 3 e raised to 3x. This will be particular integral 1 upon d square plus d minus 2 for these two factors into 1 upon d minus 3. This factor applying on e raised to 3x, which is 1 upon d square plus d minus 2. Applying 1 upon d minus 3 on e raised to 3x, this will be e raised to 3x integral e raised to minus 3x into this e raised to 3x dx, which is 1 upon d square plus d minus 2 into e raised to 3x. E raised to minus 3x into e raised to 3x will be 1. Integral 1 dx will be x. So this will be x times 1 upon d square plus d minus 2 e raised to 3x. Here, since 3 square plus 3 minus 2, which is 10, is not 0, we write the particular integral this x upon this 10 e raised to 3x. There is another way in which we can solve this. We can find particular integral using derivative. We have fd d cube minus 2d square minus 5d plus 6. We have to find particular integral 1 upon fd e raised to 3x, which is 1 upon f3 e raised to 3x, provided f3 is not equal to 0. Here f3 is 3 cube minus 2 times 3 squared minus 5 into 3 plus x, which is 27 minus 18 minus 15 plus 6, which is 0. So f3 is 0. Since this f3 is 0, what we do is we write particular integral 1 upon fd e raised to 3x as x times 1 upon f dash d e raised to 3x, that will be x into 1 upon f dash 3 e raised to 3x. Now since fd is d cube minus 2d square minus 5d plus 6, f dash d will be 3d square minus 4d minus 5. So f dash 3 will be 3 into 3 squared minus 4 into 3 minus 5, which is 27 minus 12 minus 5, 10, which is not equal to 0. Since f dash 3 is 10 and not equal to 0, we have final particular integral as x into 1 upon f dash 3, which is 10 here, into e raised to 3x, which is x upon 10 e raised to 3x, which is same as we have found earlier. Suppose we have fd equals 6d square plus 17d plus 12, which is 3d plus 4 into 2d plus 3, and function on the right hand side x is e raised to minus 3x upon 2, which is e raised to minus 3 upon 2 x. Now f of minus 3 upon 2 will be 6 into minus 3 upon 2 square plus 17 into minus 3 upon 2 plus 12. That will be 0. I request you to calculate it yourself. It's easy. So particular integral 1 upon f minus 3 upon 2 e raised to minus 3 upon 2x fails because f of minus 3 upon 2 is 0. Now from this fd we find f dash d, which is 12d plus 17, and f dash minus 3 upon 2 will be 12 into minus 3 upon 2 plus 17. 2 ones are 2 6 are, that will be minus 18 plus 17 minus 1. Now we use particular integral x 1 upon f dash d into e raised to minus 3 upon 2x, which will be x into 1 upon f dash minus 3 upon 2 into e raised to minus 3 upon 2x. So finally we get particular integral x upon f dash minus 3 upon 2, which is minus 1, into e raised to minus 3 upon 2x, which finally will be minus x e raised to minus 3x upon 2. We have fd equals d cube minus 2d square minus 5d plus 6, and we want to find particular integral of a number k, which is 8. Now particular integral of a number k will be 1 upon fd k, which will be k times 1 upon f0, provided f0 is not 0. This we write as 1 upon fd k e raised to 0x, because e raised to 0x will be e raised to 0, which is 1. So we write particular integral 1 upon fd k into e raised to 0x. Suppose we want to find particular integral of a number 8, where k is 8. We write into e raised to 0x. This will be 1 upon f0 8 e raised to 0x. Let us check if f0 is 0. So f0 will be, from this it will just be 6, which is not equal to 0. So it will be 8 into 1 upon f0, 8 upon this 6, 4 upon 3. So here particular integral is 4 upon 3. Let us see how to find particular integral when the right hand side of the differential equation x is a raised to x. We know that a raised to x is e raised to x log a. Why? Because suppose if we take logs on both sides of this statement 1, we get log a raised to x equals log e raised to x log a. Now by using the rules of logarithm, this will be x log a equals this x log a into this log e to the base e. Now since log e to the base e is 1, we get left hand side x log a, right hand side also x log a, which means a raised to x equals e raised to x log a is correct. Now, as per rule, 1 upon fd a raised to x will be 1 upon fd e raised to x log a, which is 1 upon fd e raised to log a x. So, 1 upon fd a raised to x will be 1 upon f log a into e raised to log a x. So 1 upon f d a raised to x will be 1 upon f log a raised to x, because e raised to x log a is a raised to x. So we get this formula to calculate particular integral of a raised to x. We have fd equals 6d square plus 17d plus 12, and function on the right hand side of the differential equation x is 2 raised to x. Like we have seen, 2 raised to x is e raised to x log 2 or e raised to log 2 x. So by rule, particular integral will be 1 upon fd 2 raised to x equals 1 upon f of log 2 raised to x, which is 1 upon 6 log 2 square plus 17 log 2 plus 12 into 2 raised to x. So finally, particular integral will be 2 raised to x upon 6 log 2 square plus 17 log 2 plus 12. We have fd equals d raised to 4 plus 1, and function on the right hand side of the differential equation x is cos h for x, which is a hyperbolic function. Now we know cos h for x is e raised to 4x plus e raised to minus 4x upon 2. So particular integral will be 1 upon fd x, which is 1 upon fd cos h for x, which is from this half 1 upon fd e raised to 4x plus e raised to minus 4x, which is half 1 upon fd e raised to 4x plus 1 upon fd e raised to minus 4x, which is half 1 upon f4 e raised to 4x plus 1 upon f minus 4 e raised to minus 4x. Now from this fd, f4 will be 4 raised to 4 plus 1, which is 256 plus 1, 257, and f of minus 4 will be minus 4 raised to 4 plus 1, 257 again. So particular integral will be half into 1 upon 257 e raised to 4x plus 1 upon 257 e raised to minus 4x, which is 1 upon 514 e raised to 4x plus e raised to minus 4x. So this will be our particular integral. Again we have fd equals d raised to 4 plus 1 and x equals sin h 3x, again a hyperbolic function, which we know is e raised to 3x minus e raised to minus 3x upon 2. So particular integral will be half 1 upon fd e raised to 3x minus 1 upon fd e raised to minus 3x, which is half 1 upon f3 e raised to 3x minus 1 upon f minus 3 e raised to minus 3x. Now from fd equals d raised to 4 plus 1, we have f of 3 raised to 4 plus 1, which is 81 plus 1, 82, and f of minus 3 raised to 4 plus 1, same as 81 plus 1, 82. So particular integral will be half 1 upon 82 e raised to 3x minus 1 upon 82 e raised to minus 3x. That will be 1 upon 2 into 82, 164 into e raised to 3x minus e raised to minus 3x. So this is the required particular integral. Friends, if you like this video, please click the like button. Share this video with your classmates Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.